Welcome to springlib.
Hi everyone, thank you so much for joining me. Today I'm going to be going over the polymer chain that is produced when you have these two compounds in the presence of this reagent. And we're just going to go ahead and go over the steps to get to this final product and exactly what it entails. So let's just get started. Alright, so the first thing I want to do here is actually identify this reagent and exactly what it does. So here we have AlCl3, I'm just going to highlight it here. And AlCl3 is actually a very good Lewis acid. Now what does that mean? What is a Lewis acid? So basically, all Lewis acids accept lone pairs from another molecule. So I'm going to go ahead and put that here. So they accept a lone pair. And the reason they accept this lone pair is because aluminum in this compound doesn't have an octet, and it wants that octet. So it only has 3 bonds to it from that chlorine, so it wants another set of electrons. So what is going to happen here is the aluminum is actually going to accept a pair of lone electrons from this chlorine atom right here. So what I'm going to do is I'm going to go ahead and rewrite AlCl3 here, and using electron pushing, I'm going to go ahead and use a curved arrow to show that this aluminum right here accepts that pair of electrons from the chlorine, and with that we can go ahead and combine this. So we are just going to go ahead and rewrite the structure that we now have. Alright, so now here we have a Cl, and then attached to that chlorine we have that AlCl3. Alright, and now the formal charge of the chlorine and the aluminum are actually going to be different. So the chlorine in this case is going to have a positive formal charge, and then the aluminum is going to have a negative formal charge. And one thing to note here is that when you're doing electron pushing, your formal charges are always going to be conserved. So as you can see, our starting products are neutral. And when the Lewis acid accepts that lone pair, chlorine gets a positive and then aluminum gets a negative. So the positive plus the negative, that still gives us a neutral charge. So that's just something to remember, that the formal charge of your compounds when electron pushing is always going to be conserved. Now we have this compound, and one very important thing to note is that this guy right here is a very good leaving group. So I'm just going to go ahead and highlight this in blue here, and I'm going to put good leaving group, and I'm just going to do LG to abbreviate leaving group here. And then I'm also just going to use another arrow to imply that this guy is going to be kicked off. Alright, perfect. So once that's kicked off, now we get this guy. Let's go ahead and rewrite this out. And once this leaves, we get something pretty important. We get our carbon cation intermediate. So a cation is always a positive charge, right? And it's called a carbon cation because it's this carbon that has that positive charge. And then that AlCl4 now is left, so I'll just go ahead and write that here since it's still floating around. I'm going to go ahead and put a negative charge on this aluminum. Perfect. And now that we have that carbon cation intermediate, this is going to be our electrophile. So electrophiles are always electron deficient, and what they do is they attract electron-rich molecules, which makes sense, right? They're deficient in electrons, so they want more. So they attract electron-rich molecules, and in this case, our electron-rich molecule is going to be attracted to is going to be this diol here. So I'm just going to go ahead and rewrite this over here. Give ourselves our hydroxyl groups. All right, perfect. And then it's just going to grab one side of this. It doesn't really matter. So I'm just going to draw these electrons there. And then these electrons are going to be attracted to this carbon cation. And now we can go ahead and rewrite that. So we have, again, this first compound we started with. Then we have that carbon-oxygen bond that's now formed here. And this still has this H attached to it, and keep that here. And then we can go ahead and add that cyclohexane ring we have. And then add that group. And then here the oxygen has a plus charge, since formal charge of oxygen is 0 when it has 2 bonds and 2 lone pairs, and here it has 3 bonds and 1 lone pair. So, and with this molecule, we still have this now base still floating around. So this is the conjugate base of our Lewis acid. So I'm just going to go ahead and rewrite that down here, because what that's going to do is it's going to remove this proton from our oxygen. So again, this has a negative charge on it. Now we can go ahead and do some more electron pushing. So a chlorine on here is actually going to grab this H, and then we have more lone pairs going back here. And now we can go ahead and write out our product that is now deprotonated. So we have this guy. And now we have this O here, and it no longer has that hydrogen attached to it, since that base from the Lewis acid went ahead and grabbed that. So now we have our other ring attached here, and then again our other OH group over here. And also with this, since the H grabs the chlorine, as mentioned, we're left with a hydrochloric acid, so HCl, and we're also left with our starting reagent. So we take one chlorine away from that AlCl4, and we're left with our starting reagent, which is AlCl3. All right, perfect. And now this process actually repeats itself over and over and over. So what happens here is you get a very long chain, because you're left with your starting reagent, so then you'll get another carbon cation intermediate once our reagent grabs this chlorine, and that then leaves, because it's a good leaving group, which leaves us another carbon cation intermediate, which then can attach to another one of these diol molecules. As you can see in the final product here, we have this guy, and this N right here indicates that this is a polymer chain. So the end product here, and we're going to have a long chain of this particular molecule, and it's going to go back and forth from this benzene ring to this cyclohexane ring, and then we're also going to have these oxygens in here. So let's just go ahead and draw that real quick. I'll go ahead and do it in blue here, just so we know that's our final answer. All right, and then our brackets are going to go right here, because that kind of indicates where it keeps going, and it just keeps alternating between these two compounds. All right, so this indeed is our polymer chain that is going to be produced right here when we combine these two reactants with this reagent, as mentioned. And another thing to take note on is this is actually a polyether. So we know the ether functional group appears like this. So you have an oxygen between two R groups. So here we have two ether groups, of course, so that's why that is a polyether chain. So another thing to note here is that there's 3 specific steps that take place here. So let's go ahead and determine those. We have 3 steps. Our first one is that formation of our carbon cation. All right, and then second, we have the growth of the polymer. So the growth of the polymer, that's when this happens. So that's when we get a carbon bonding to something else. So in this case, it's an oxygen. So here we get that carbon-oxygen bond. So growth of polymer. And then third, we get this deprotonation step right here. So that's kind of, as they call it, a terminating step, because after that happens, that's when this process can repeat right here. So that gives you kind of your final products, and then those products can go ahead and react with each other again. So here we have deprotonation. Alrighty, and that's all I have for you today. I really hope you find this video helpful and helps with your understanding on just how this process works. And thank you so much, and I will see you guys next time.